on to our second talk, which is on learning mechanisms in Q weighting. And I think Vsevolod Kapatsinski will be presenting. This is work with Adam Bramlett and with Kaori Idemaru. Thank you.
All right, thank you so much. I'll talk fast because, oh, it's over there. Right, so we're talking about learning mechanisms in Q weighting and specifically phonetic Q weighting. It's part of a broader project that tries to look at language learning as basically a type of learning, and so providing implications for the main general learning theory. And so the research strategy is to derive surprising or unique predictions of models in learning theory that distinguish one model from another and then test them with behavioral experiments on language. Today, we are going to be using phonetic Q weighting as a window on how prediction error is used in learning, comparing a classic error-driven learning model by Skorla and Wagner, which is often called the standard theory of associative learning, and the new model that we developed based on a set of experimental data that I will tell you about next. So the Skorla-Wagner model basically deals with this kind of situation where you've got a bunch of environmental cues and you're trying to predict events in the world called outcomes. And so when one of these outcomes occurs, when a set of cues are present, then you update the associations between the present cues and the outcome using this formula, which basically says that you are just increasing the weights by the difference between 1, which is how activated an present outcome should have been, ideally, and the sum of the Q weights from the present cues to that outcome, which is how much it was activated by the present cues, given your current beliefs. So this term then is the prediction error. It's the difference between correct activation and the activation that the outcome actually had. When it's absent, you do the same thing, except you subtract the activation of the outcome from 0, which is the correct activation for an absent outcome. So here you would do the first equation for outcome 1 and the second equation for outcome 2. Basically, to briefly summarize, you're updating connections by strengthening connections between present cues and present outcomes and weakening the ones between present cues and absent outcomes in proportion to prediction error. As a result of that, if Q outcome co-occurrence is random, so if you're getting 50-50 feedback, for example, for a particular combination of Qs, then the weights should be kind of middling. So what we are testing here is how do you give up on a Q that used to be predictive but is no longer predictive. And whether you can downweight a predictive Q without upweighting something else. In Skorla-Wagner, you can actually downweight a predictive Q without upweighting other Qs. And so you can give up on a predictive Q even if there are no other Qs to rely on for prediction. We test this prediction with phonetic Q weighting. So that is basically weighting the Qs that define, for example, the difference between the word pair and the word bear. In English, if you look at English native listeners, they will primarily rely on an acoustic dimension called voice onset time, or VOT, whereas native Korean listeners will rely primarily on F0, a different acoustic dimension, which is basically pitch and the beginning of the next vowel. So we are asked, in this 2019 paper, we asked how we can turn English listeners into Koreans. Or, in other words, how can we make them downweight VOT to adapt to, for example, Korean accented English? So what would that mean? So basically, before training, an English listener behaves like this. When they hear a sound with a VOT of 35 milliseconds, they will basically always say pair, regardless of F0. And if VOT is short, if it's 15 milliseconds, they will basically always say bear, regardless of F0. But if a VOT is middling, if it's 25, then they will decide based on F0, right? They'll say pair if F0 is high and bear if it's low. For Koreans, you will get a difference like this with English. So after training, we want them to think that F0 to 50 is always pair and F0 180 is always pair, regardless of VOT. So turning VOT, downweighting VOT relative to F0. So the question is it enough for VOT to cause error during training? Or is it also necessary for F0 to be informative during training and predictive of the feedback? Just a bit of terminology, individual F0 and VOT values here we'll call Qs, and the F0 and VOT kind of lines or dimensions we call dimensions. So what are these physically? Well, VOT is the length of this aperiodic puff of air from after your mouth opens to before you start vibrating your vocal folds. And F0 is the pitch that happens at the end of this interval. So these are the dimensions we're looking at. So in training, they got 4 pictures, a peer, a pair, a bear, a beer, and a bear. Arranged on a computer screen. They would hear stimulus with some VOT, F0, and vowel. They click on the picture they think that sound is referring to and receive error feedback like this. And test is the same as training, but no feedback. So there should be a sound. But so you would see these pictures, you would hear bear, you would hear bear, and you would if you click on the pair, then you get feedback that says it's incorrect. If you clicked on the bear, then you would just get the bear remaining on the screen like this. Sorry, there's no sound. So there were 3 training conditions in the 2019 paper. There was a control condition that's basically like English. 35 is always pair, according to feedback. 15 is always bear, regardless of F0. There was an informative F0 condition where F0 was perfectly predictive of the feedback and VOT was uninformative. So you got 50% bear and pair for every value of VOT, but it was predictable from F0 of the stimulus. And here, Briscoe-Wagner predicts that you should upweight F0 and downweight VOT. The interesting condition for us is this one, where VOT is still uninformative. So for every value of VOT, you get 50% BA and 50% PA feedback. But F0 is constant. And so switching your attention to F0 and upweighting it would do nothing, right? You would still be wrong 50% of the time. So Briscoe-Wagner model would downweigh this even in the constant F0 condition because it would produce a more accurate belief system where each value of VOT basically is equally likely to map onto BA and PA, even though this would not reduce your error in behavior. So the prediction is kind of like this. On the left, we have the predicted responses for VOT 15, 25, and 35. On the right here, you have for F0, 180, and 250. And you see that there's going to be a decrease in the VOT effect of the difference between these values of VOT in informative F0 condition and an increase in the F0 effect. And then in the constant F0 condition, the F0 should not be upweighted because it's randomly paired with voicing, but VOT should be downweighted according to Briscoe-Wagner. So what are the results? So these are results in the same exact format. You see that in the control condition, basically VOT is much more important than F0. There's a much bigger effect of VOT than of F0. In the informative F0 condition, this basically almost reverses. And that's as expected. But then in this constant F0 condition, what you see is basically no downweighting of VOT. Right, VOT, they're treating VOT just as they do in the control condition, even though it's paired with BA and PA randomly in training. Okay. So our conclusions from this study were that downweighting of VOT cues occurs only if relying on other cues would be better. And the proposed solution that we came up with is to have learners reallocate attention from VOT to F0 only if doing so would reduce prediction error. The way our model did that is to maintain a space of possible basically regression weights for VOT and F0 dimensions, representing how much attention is paid to VOT versus F0 in phonetic categorization, and just keeping track of how accurate each of these combinations of regression weights is over the course of training. Then, when deciding on what they're hearing, the person would choose the combination of VOT and F0 weights that has had the highest accuracy in their experience. So this is basically the model says that you maintain this kind of space of possible weights of VOT and F0 and their relative predictive accuracies. And you pick the combination of VOT weight and F0 weight that has the highest accuracy to classify a particular sound. Okay. So there are two differences between these models. Riskola-Wagner learns associations between specific cues, like VOT equals to 5 milliseconds, and outcomes like ba and pa, whereas Hick learns how much weight to allocate to dimensions, like VOT, not individual values, like VOT is 5 milliseconds. And Riskola-Wagner downweights cues whenever they become less predictive than they used to be, whereas Hick will switch to a new combination of weights only if that combination of weights is better than the other combination of weights. That is why it doesn't learn in constant F0 condition. It doesn't change its behavior. So in the current study, we were interested in whether people would downweigh dimensions that are predictive even when they encounter just a single value on that dimension. In the previous study, they were encountering a range of values along the dimension, so they had information that the dimension should be downweighted as a whole. Here, we're just giving them one value like VOT5 in training. So some people were trained on VOT5, some were trained on VOT25, and some were trained on VOT45, and the feedback was always 50-50, as in the other study. And the reason we have 5, 25, and 45 is that there's different amounts of prediction error for English listeners in these different conditions. When you are listening to a VOT5 stimulus, like bear, you must always think it's bear. Right? It means, the animal. And so there's a strong error signal when feedback says that the ba response is wrong and it really was pear. In 45, it's the opposite. You always think it's pear, but when it's actually bear based on the feedback, then you get a strong prediction error signal. Whereas in 25, you were already expecting 50-50 because that's what it is in English. And so there's no prediction error, essentially. So there should be more learning in VOT5 and 45 condition about the unexpected outcomes than in the 25 condition. Now then we also manipulated the distribution of F0 kind of in a similar way to the other study. So here you see conditions where F0 is predictive, but we also had conditions, and here, as I said before, you would expect upweighting of F0 and downweighting of VOT according to both models. But we also have had conditions where F0 was constant and a condition where F0 was variable, but not predictive of the response. So you would get 50-50 feedback for both values of F0, like for both values of VOT. Then we tested them on new values of VOT and F0 that were in between these training values, right? That were equally different from the training values in different conditions. So they need to generalize from 5 to, let's say, VOT15 and VOT35, and from 45 training to VOT15 and VOT35. So here's the results. In the predictive F0 condition, and here you're looking at pre and post-test. So this was another difference from the other study. We did a pre-test as well as a post-test. And you see the log odds of PA response here for VOT15 in red and VOT35 in blue. And what you see is that when you were trained on VOT5, you get an increase in responding with PA to VOT15. And when you were trained on VOT45 being sometimes BA and sometimes PA, you get an increase in the BA responses for VOT35. So they're responding more with the unexpected response based on their prior beliefs to cues that are similar to the cue on which they were trained. And there was a little bit of upweighting of 0 in this condition also as predicted. Now, in the other conditions, we see something that we did not expect based on our previous study. So here in the constant F0 condition, you still see a change for people who were trained on VOT45 in how they were treating VOT35. So they were still producing more of the unexpected response to that cue, even though there was no significant upweighting of F0 in this condition. So this contradicts our model because there's downweighting without upweighting here. And we have this even more strongly in the unpredictive F0 condition, where we see this with both training on VOT5 and VOT45. In all cases, you also see that there's more learning from VOT5 and VOT45, where there is error, there's a strong error signal than in VOT25. And again, here we see downweighting of VOT restricted to the similar Q, the Q that's similar to the Q that they were trained on, but no upweighting of F0. All right, so then we can test this more formally to see whether actually, excellent, there are differences in the amount of learning for the value of VOT that was close to the training value and the value that was far away. Right, so for VOT5, the close value is 15 milliseconds, and for VOT45, the close one is 35 milliseconds. So we look at how much learning there is in these close values relative to how much learning there is in the far values. And here, because it reweights dimensions, says that basically there should be equal amounts of learning for near and far values because you know, you're reweighting the whole VOT dimension. Because what you're learning here is that VOT doesn't matter, you should be thinking both that 45 is BA, and you should be using that to infer that 15 could therefore be PA, because the slope of VOT then is small, right? VOT doesn't matter, so all unexpected responses for values of VOT should be increased. Rescorla-Wagner thinks that because 45 is BA, then you're generalizing from that Q to similar Qs. So 35 might also be BA, but 15 is really far from 45, so you're going to get relatively little generalization. And that generalization is going to be, again, in favor of that a priori unexpected response that you got in training, and not in favor of the opposite response. So what we got was basically was this, right? So here we're looking at the probability of choosing the response that's consistent with dimensional reweighting for far and close values in the three conditions, predictive, constant, and unpredictive F0 here. I'll walk you through this because it's kind of complicated. But basically, we see very little learning from pre-test here to post-test here for the far values, right? You see that these are basically the same, right? So we're not seeing a lot of dimensional reweighting based on a single Q, right? There's mostly just learning about these close values, which is consistent with reweighting the individual Qs that they encountered and generalizing from them. So that's consistent with Rescorla-Wagner. There's also learning about the close value even when there's no other Q to rely on. So they're giving up on this value of VOT in a way. They're reducing how predictive it is, even though F0 is useless during training. And that's also consistent with Rescorla-Wagner. But on the other hand, there is more learning about VOT when F0 is predictive. So in fact, if you do have F0 being predictive, you get more downweighting of that close value of VOT. Okay, so that's not consistent with Rescorla-Wagner and consistent with our model. So in conclusion, there was learning from 50-50 feedback when this 50-50 feedback was unexpected for the experienced value of VOT. So for 5 and 45, they learned from random feedback that those values of VOT are not as favorable to PA and PA respectively. And as in our previous study, we saw that there was more VOT downweighting when F0, a secondary Q, was predictive of the feedback. This is consistent with our reinforcement learning model. But unlike in that study, we did see some VOT downweighting when VOT and F0 were both unpredictive, and that's consistent with Rescorla-Wagner. So what I think is going on here, or what we think is going on here, is that downweighting VOT here is basically just reweighting the Q outcome associations of the experienced VOT value, like VOT45, because they're just encountering a single value. They're not generalizing to all values of VOT. They're just generalizing to similar values. They're not learning that VOT in general is uninformative. They're reassociating 45 and similar values with BA, or 5 and similar values with PA. But this is basically giving up on a predictive queue, right? Because these are highly predictive queue based on English experience. And giving up on a predictive queue, like giving up on a predictive dimension in our other study, is easier when you have something else to rely on, right? So if you don't have anything else to use to predict BA or PA, you might as well stick with your previous Q weights because there's no other combination of Q weights that's better. When there's when you can rely on F0 to make these predictions, then you're more willing to give up VOT. All right, thank you very much. And here's my references, and thank you.
Great, thank you. We have time for questions. I feel like I can never see who's approaching the mics. Actually, while people are thinking, there's actually a lot of really interesting data. Can I ask? I have a thought that's not a fully formed question. I was curious because you had the VOT was a binary choice ultimately, BA versus PA.
Yeah.
I was thinking, what if you had a three-way distinction, like let's say place of articulation, like BA,
Yeah.
that wouldn't have a secondary dimension. I was trying to think of if there was a secondary dimension to test, but I was curious because especially with like if you heard a very short VOT and then they were told it's actually a voiceless stop, like this, you could just think of, oh, it's the other response type of this binary with a binary scale. But if you had a three-way pattern, then you couldn't do some kind of, oh, it's the other one type reasoning. I don't know if that makes sense, but I was curious if you had any thoughts on porting it over to a three-way distinction as opposed to two-way.
Yeah, three-way distinctions are interesting also because you couldn't just then have a model that has a linear kind of regression weight for the dimension. Yeah, so you'd have to either kind of parse it into two dimensions, right? So for something like F1, you know, and the vowel space, right, you would have to either like somehow break it up into binary contrasts, right? Or be able to learn nonlinear relationships between the dimension and the vowel categories to the extent that you are doing kind of dimensional learning, which I think actually, I mean, we don't have a huge amount of evidence that there is dimensional learning beyond just sort of individual Q reassociations. And there are models that can successfully do this kind of vowel learning. For example, Burzma and Haman's model just does it by reassociating individual Qs across the vowel space. So I think it's an open question, you know, how much we do this kind of dimensional reweighting still.
Thank you. Oh, sorry. See, I always have to face the other way. Please go for it. But thank you.
Hi, thanks. It was really interesting. Now, my question is not going to be like super related to the problem that you've applied, you know, these two different models to here, but maybe you'll indulge me and just tell me what your thoughts are. So, you know, obviously your task is all about learning and what happens, you know, how can we best explain the type of pattern we see in a learning task? But what about processing, right? Or in other words, you know, does it make any sense to derive predictions from these models and apply them to online processing? And so, you know, in that case, would you predict, or would these models predict that, you know, if you generate a strong expectation for something which turns out to be correct in a particular context, at the same time you learn, well, at the same time in that context, you would also, you know, online, like strongly suppress another possible option. Does that make any sense? I don't know if it does, but in other words, can you apply this difference between the models to processing as well as learning?
Yeah.
Do you have to? Maybe you don't have to explain the learning effect.
Yeah, that's an interesting question. I mean, for our model, there is, because we are relating it to attention allocation. In a way, it does kind of ignore, the other value once it's decided that this value is, so the other dimension, right? So if it thinks DOT is much more predictive than F0, then online, it's going to be using DOT a lot and not attending to F0 so much, which then in turn has more consequences for learning downstream, because then it's going to be hard for it to learn that F0 is actually doing something unexpected, potentially. We kind of get around that prediction by saying that actually it derives predictions from all the possible combinations of DOT and F0 weight. But you could think of a model where that's not the case and where it doesn't have that space of F0 and VOT weights, in which case it would then say, yeah, if you think VOT is important, then you're ignoring F0 and you're not going to learn much about F0 from now on. Krushke's models work that way, for example. Riscorlo-Wagner, I think, would say it doesn't have this kind of attentional component, so it always attends to everything, regardless of how predictive those things are.
Thank you very much.
Thank you.
Hi, Eleanor Shadroff, University of York. I noticed you were tying all of these to real words of English, and I was wondering if you would predict similar effects if you had used nonsense words. So I can see this having implications for talker adaptation, but what about potentially new category formation that might still overlap a bit with their native language?
Yeah, that's interesting. Yeah, we haven't tried this paradigm with nonsense words. I would expect it works.
Well, differently than what you observed here, or in the same way?
No, I think it would work the same. Yeah, I mean, it would be interesting. I think, from these models' perspective, it doesn't really matter from where the feedback comes from. So they wouldn't really care whether they're pseudo words or real words. But I think it is an open question, like how broadly do people generalize here, right? Because do they generalize to all other words with ba and pa? Do they generalize to, other vowel contexts? Do they generalize to other speakers? Kaori Idemaru has some related work with a different learning paradigm where they flip the co-occurrences between VOT and F0. And there they find that generalization is actually very limited. So they're not generalizing much to new speakers or new vowel contexts and so on, although they do generalize, I believe, to new words with the same vowel context. So yeah, we don't really know how far people will generalize. In some ways, you kind of hope that they wouldn't generalize too broadly, from 5 minutes of experience. You don't want to override your long-term DOT and F0 weights. You want to learn something specific to that context. So yeah, that's all I can say about it.
Thank you so much.
Last chance, if there's any remaining questions. All right, let's thank the speaker again.
Thank you.